What is up, you guys? Welcome to this solo cast episode. Thank you to Ben Greenfield for the questions, which I will be answering in this solo cast episode. As many of you may know, I've written the book, The Carnivore Code. If you're watching the video, you can see it there behind me. This podcast will be released the first week of August 2020 when the second edition of my book is now live. So if you enjoy this information, check out the book, thecarnivorecodebook.com. If you guys are new to this, if you haven't heard me talk to Ben or about the carnivore diet, Ben and I have done two previous podcasts on the carnivore diet that you may want to check out in addition to this one. So I was on Ben's podcast in March of 2019. And then last year or earlier this year, when the first edition of the book came out, I did the first solo cast on Ben's episode, on Ben's show, in which I answered some reader questions about the carnivore code. And after Ben read the book, he sent me a list of questions that he had about the carnivore code. And that is what I will be diving into more specifically today on this solo cast episode. As many of you know, Ben is a student of this stuff in biochemistry, so some of these questions are pretty detailed. I'll try and break them down as clearly as I can. There's a lot of good nuance here that I think will bring you guys a lot of value. If you are more interested in a broad overview of the carnivore diet, I'll give you a 3-minute summary now before I dive into some of these finer points. The carnivore diet is an idea of an animal-based diet in contradistinction to plant-based diets of today. The theses that I advance in my book, The Carnivore Code, are twofold in broad terms. The first is that animal foods, specifically red meat and ruminant animals, have been incorrectly vilified for the last 70 years, mostly as a result of incorrectly done science based on observational epidemiology. We have Ansel Keys to thank for that in many ways. I've done a great podcast on my show with Nina Teicholz, who wrote A Big Fat Surprise, in which we break down many of the myths surrounding saturated fat. So I probably will not get into saturated fat in this episode today, but if you want to know why we have such a bad misunderstanding of saturated fat, listen to that episode on my podcast. We go into the details of saturated fat, why it's actually very healthy for humans. I'll probably get into it a little bit today with stearic acid later, but that is a big, big misconception. There are many other misconceptions regarding red meat, that it will cause cancer, that it will cause heart disease, that it will shorten your life. Some of those I will address today. They are all addressed in my book, but they are all false. None of them are supported by real interventional science, actual experiments. They are false claims made based on observational epidemiology that has been widely misinterpreted and is inherently flawed. Ben and I have talked about this in the past on previous shows, so refer to those. So the first thesis of the book, The Carnivore Code, is that red meat and animal foods, nose to tail, organ meats, which I'm going to talk about a lot today, are critically important in the human diet. They're part of every human's diet if we wish to be healthy and optimal, and they should not be shunned based on incorrect science. Embrace the red meat especially, and know that you need those meat and organs in order to thrive. Ben, I know, is becoming more and more a fan of organ meats. He and I have eaten many nose to tail meals in the past together with great enjoyment, and there are many amazing stories of that I'll let him tell you at some point in the future. The second thesis of the book is that plant foods exist on a toxicity spectrum. Plants are rooted in the ground. They have no defenses other than the toxins they have evolved. This is not really conjecture. This is botanical science. In the Carnivore Code, I discuss multiple studies showing there are thousands and thousands of plant toxins that are present in plants, and these can be harming us. My goal in writing this book is not to convince everyone to stop eating all plants. It's to empower you to realize twofold, as I'm saying here now, that red meat and animal foods are the most nutritious foods on the planet. By that I mean containing the most bioavailable sources of all the nutrients humans need to thrive. And number two, that if you're not kicking as much butt as you want, you may be well served by considering the plant foods you are eating on a toxicity spectrum, which I also outline in the book, and eliminating the plants that are most toxic, that may be harming you in a variety of ways. Plants make defense chemicals. This is undeniable. And again, I get into all that in the book. It's a very comprehensive book. There are over 650 references, and that is a broad strokes outlook on the way that I think humans really should be eating. The first part of the book is about evolution. We talk about the human brain. And I talk about the human brain in the book at that point, and I talk about how it's gotten very big very quickly over the last 2 million years, primarily as a result of humans eating meat and hunting. I'm going to answer some questions Ben had in regard to that in this podcast. And secondarily, I talk about the fact that when we began agriculture, our health went south very quickly. And there's very good evidence that this is the massive change in the nutritional density of our foods that accompanied that as we were hunting less. And I will talk about that specifically in this podcast because Ben asked a question about that. The second part of the book is mostly about plant toxins. I break down individual types of plant toxins. I talk about polyphenols, why I think we've got this all wrong. Ben and I may respectfully disagree here, but I do make what I believe is a very strong case for this in the book. And I would love more discussion with this in the future. I talk about oxalates and lectins and salicylates, and I talk about all kinds of things like that that are harming us. Isothiocyanates, which I will talk about today, which are things like sulforaphane and goitrin, and how these plant compounds can affect hormonal balance, they can affect nutrient absorption, they can affect our gut, and really wreak havoc in a lot of us if we are not aware of how present in our diet they are, how we might detoxify them, and how some of us might be more specifically sensitive to them than others, and they can be causing us great harm and suffering. The third part of the book is about debunking myths. In the book, I talk about, I debunk all the myths I could think of with meat, that it shortens your life, that it causes cancer, that it causes heart disease, and that you need fiber to poop. So all that is in the book. I won't get into all of that today. I could never do that. It would be a 6-hour podcast, but rest assured it's in there. And in the fourth and final part of the book, I outline a very clear perspective, a very clear model for how to eat a carnivore diet. I outline 5 tiers of a carnivore diet, which give the reader a sense of how to do this that works best for you. And some of them include plants. A tier 1 carnivore diet includes plants. I call it carnivore-ish, but it gives you a toxicity spectrum. And the foods that I believe are least toxic are includable. They are able to be included on a carnivore-ish type diet. Ben himself has often said that he's eating carnivore-ish. I don't want to put words in his mouth, but I think that he would agree with this, that he is thinking about making the majority of his diet animal foods and organ meats, and then eating the plant foods that agree with him the most, and thinking about the toxicity spectrum of those plants. So that is a tier 1 carnivore diet, all the way down to or up to a tier 5 carnivore diet, which is a nose-to-tail carnivore diet, much like what I eat. I will describe my diet in detail toward the end of this podcast. You can also find lots of information about how I eat on my website, carnivoremd.com. And I talk about it in the book, which you can get at thecarnivorecodebook.com. So the last chapter of the book is about regenerative agriculture. Ben didn't have any questions about this. I've done a podcast with Rob Wolf and Diana Rogers. I talk about this in detail in my book as well. And the take-home message here is that animals raised properly, ruminant animals raised properly in a regenerative fashion, sequester carbon, or part of a cycle, a natural ecosystem cycle that sequesters carbon into the soil and makes the soil more fertile. It increases the microbiome of the soil, the mycorrhizal networks with the plants and the roots that allow plants to grow more robustly, feeding the animals, leading us to be healthier because we are eating healthier animals, and leading the soil to continue to provide plants with nutrients, which provide animals with nutrients, and the ecosystem works. The simple fact of the matter is that the one metric that I believe will determine the persistence of humans on this planet is soil carbon. And the best way, the only way that I'm aware of to increase soil carbon is by having plants and animals together on a patch of land, which requires proper regenerative grazing of ruminants on grasslands and in other ecosystems. You cannot do this with monocrop agriculture. We are in a hell of a problem right now with the way that monocrop agriculture is depleting our soils, and this is an absolute catastrophe for humans long term. So be aware of regenerative agriculture and the way that that treats the planet differently, tries to recapitulate, to recreate these grassland ecosystems in which ruminants have always lived and that have created some of the most fertile soils in the world. The problem is that these soils have now been farmed to oblivion with monocrops, and we're trying to regenerate them as fast as we can to get these lands more fertile again. Our blood, our future is really in the soil, and the way to create healthy soil is with regenerative systems that include animals responsibly. So that's an outline of the book for those people who are not familiar with this concept. Like I said, Ben and I have done multiple podcasts in the past that you may want to refer to. And without further ado, I will dive into some of Ben's questions, and we will get going on this solo-sode. As I get into these questions, I also just want to reiterate how much I appreciate Ben Greenfield. We've definitely got a little bromance going on, and When you guys see the level of detail that Ben is asking me in these questions, it's pretty freaking amazing and impressive. So I appreciate you, Ben. I appreciate your followers. I appreciate all you guys listening to this. And I appreciate so much that Ben took the time to read the book cover to cover and send me what is a pretty darn detailed list of questions, which I think you guys will appreciate in a big way. So enough of the bromancing. First question from Ben is, you use the term rabbit starvation a lot. What's that mean exactly? Is there a magic ratio of protein to fat to shoot for? So fantastic, good question to start off with. One of the main things I think about with a carnivore diet when I'm starting is, how much protein should someone be eating? And I get this question a lot. How much protein should I be eating? When I'm designing a carnivore diet for someone, I'm also thinking about how much protein they're going to eat on a daily basis as the center of their diet. I talk about this in the carnivore code. And as a baseline, I have people start with 1 gram of protein per pound of goal body weight. Now, there's a lot of questions about what's called rabbit starvation, which is essentially protein poisoning. This is going to get into some complex biochemistry. For all of you guys listening to this, either on my podcast or Ben's podcast, know there is a video version that accompanies this podcast on my YouTube channel. I'll give it to Ben if he wants to post it on his YouTube channel as well, in which I will be doing screen shares of many of the articles and technical graphics that I will use throughout this podcast. Some of this may get a little bit in the weeds. So the idea with rabbit starvation is this: if humans eat only protein or a certain amount of protein without enough fat and or carbohydrates, we do get hyperammonemia. We get high amounts of ammonia in the blood, which leads to essentially starvation in the setting of protein. So it's called rabbit starvation because rabbits are so lean. If you only eat rabbits or squirrels or small rodents, you will die because you need fat and carbohydrates in addition to the protein in order for human biochemistry to work. That is the high level. Now, how much fat do you actually need? No one knows for sure, but I think most people will know if they've done bodybuilding competitions or other very low fat and semi-low carb diets that you can lose a lot of fat doing this, but there is a cliff off which you will roll metabolically and hormonally if you extremely avoid fat and carbohydrate when you are pushing protein. In the short term, it can work. This is called protein-sparing modified fasting, but it's essentially rabbit starving yourself. This is lean chicken breast diets, lean red meat diets, do not work long-term unless you have fat and carbohydrates. And this is because of the way the body's biochemistry works within the urea cycle. When humans consume proteins, which are molecules which have a nitrogen group, that they have multiple metabolic fates. They can become building blocks for muscles and tissues of the human body, whether it's collagen or actual muscle fiber. All of our body is composed of many proteins, which are composed of amino acids. Amino acids can also be used for metabolism. They can be oxidized to glucose or they can become ketones. There are some amino acids which are dedicated and can only become ketones. These are leucine and lysine. I'll show a graphic that shows this. There are some that can only become glucose through a process called gluconeogenesis, which I'll review in a moment as well. And there are some that can do both. But let's take a look at the urea cycle real quickly. Once proteins have been broken down into one of those fates, whether they've become a ketone body, which I'll review, whether they've become glucose and gluconeogenesis, they are oxidized and there is a nitrogen group left. And that nitrogen group here combines with carbon dioxide and enters the urea cycle. This is how the body gets rid of NH4+, which is ammonia. Not a good thing to have hanging out in the human body. It's fairly toxic to the human physiology. There are a number of enzymes involved in the urea cycle, which you can see in this graphic. The first one is carbamyl phosphate synthetase 1, which is really the rate-limiting enzyme. You can see that this nitrogen, this NH4, this ammonia combines with carbon dioxide, becomes carbamyl phosphate, then citrulline, arginosuccinate, arginine, and ornithine. And at the end of this product, of this cycle, is urea. So what you'll see here is that a number of amino acids come in here. Citrulline, aspartate comes in. There are a number of enzymes in the cycle, but urea is what's produced. And a urea is a water-soluble form of this nitrogen, which we excrete in the blood and the urine. So if you get a blood work panel and you see BUN, that is your blood urea nitrogen. If you eat lots of protein, you will see your blood urea nitrogen go up because your body is upregulating this urea cycle to excrete the urea. The thing that's very interesting about humans is that many of these enzymes, specifically arginase and arginosuccinase, can only be upregulated to a small extent as we increase our protein consumption. That is to say that in obligate carnivores, things like lions, cats, felids, they can actually upregulate those enzymes infinitely. Our biochemistry is different. We have a ceiling to which we can upregulate those enzymes. So there is both a ceiling to the amount of protein that any human can consume physiologically, and because of the energetics of the urea cycle, there is nuance here as well. And this nuance is that the urea cycle requires ATP inputs. ATP is adenosine triphosphate. In order to run the urea cycle, we use 4 units of ATP. So I'll show this graphic, which shows the inputs of ATP into the urea cycle. We're getting in the weeds here. I promise we will come back up for air in a moment. You can see there are 2 ATP in the first step, which occurs in the mitochondrial matrix, and there are 2 more ATP used in this cytosolic step of the urea cycle. So total of 4 ATP inputs into the urea cycle. Why is that important? Well, we require energy to break down proteins or to break down ammonia into urea. Why does that matter? Because we also require energy to do gluconeogenesis. So if you guys are really interested in the process of gluconeogenesis, you will know that the conversion of essentially amino acids into glucose is the reverse of glycolysis. And if you reverse glycolysis, that process requires ATP inputs. So we have, if you are eating only protein, which will give you amino acids, in order to make glucose, which your body needs, you are going to have to do gluconeogenesis, which requires the input of ATP. And then you have ammonia, which is produced, which is also going to require the input of ATP to get rid of. So the problem then becomes essentially one of energetics, that if you are trying to run human biochemistry on amino acids exclusively, you can do it up to a point, but you cannot get all of the calories that humans need from that, because the conversion of amino acids to glucose requires ATP inputs, and the conversion of the ammonia produced from the breakdown of amino acids requires ATP inputs to do the urea cycle. So herein lies the problem. Herein lies sort of the thermodynamic conundrum for humans if we try and do this, and herein lies the major toxicities which result in hyperammonemia. So the best paper that I have found on this, these will all be in the show notes at Ben's episode and linked on my episode, is this one, a review of issues of dietary protein intake in humans. This is from the International Journal of Sports Nutrition and Exercise Metabolism. And as they say in the introduction, in the abstract, dangers of excessive protein defined as when protein constitutes greater than 35% of total energy intake include hyperaminoacidemia, hyperammonemia, hyperinsulinemia, nausea, diarrhea, and even death, in quotations, the quote, rabbit starvation syndrome. And this is essentially because, as they mentioned in this paper, those enzymes in the urea cycle that I talked about earlier have a ceiling in humans. They cannot be upregulated, and we run into this energetic bottleneck by using exclusively amino acids for our metabolism. We run into this ceiling, which is called the maximum rate of urea synthesis, MRUS. And there is a chart that they have in this paper. There is some individual genetic variation based on your genetics and also based on how big you are. So these are referenced in previous papers, but I will show in the video here the body weight maximum rate of urea excretion chart. For those who are listening, across the top is the body weight in kilograms. On the vertical axis is the mean rate of urea excretion in milligrams of nitrogen per hour per kilogram, okay? And you can see that I am 170 pounds, which would be approximately, let's just say, I'll do the conversion, 77 kilograms. You can look at this chart. Let's call me 75 kilograms or 80 kilograms in here, somewhere between 70 and 80 kilograms across the x-axis. You can go down this, and you can see that for someone who is between 70 and 80 kilograms, their daily protein maximal intake based on the mean rate of urea excretion, which is a genetic variable across the y-axis, ranges from 221 grams a day to approximately 301 grams per day. So this is what we know about human physiology right now, that someone of my size can easily maintain normal metabolism, provided I have fat and or carbohydrate with 220 to 301 grams of protein per day. If you're bigger, you could do more. But even if you are getting adequate amounts of fat and carbohydrate, there is a chance that you run into the possibility of hyperammonemia in your blood, which is not a good thing, if you exceed that amount of protein. And it's basically determined on your kidney and your liver's biochemical ability to excrete urea in the urea cycle, and how many other energetic intermediates you're getting from the fat and or carbohydrates. So this is sort of the ceiling for protein intake in humans. You can find it in this paper. This paper will be linked, but the real concern, like I said, is hyperammonemia. You don't want this. If you are eating a ton of protein in your diet and you see your AST, which is aspartate aminotransferase, or ALT, alanine aminotransferase, these are liver enzymes, or if you see these bump, if you see your GGT bump, which is gamma glutamyl transferase, or you see your BUN consistently high, you may be eating too much protein. I'm not familiar with any research that shows that greater than 1 gram of protein per pound of goal body weight is needed for maximal muscle growth. Now, back to Ben's question, rabbit starvation is when you don't get enough fat and or carbohydrate to provide other ATP to run these detoxification processes. Now, as you know, glucose, carbohydrate, can be broken down via glycolysis and then enters the Krebs cycle to form many intermediates of ATP, which run our metabolism. Fat can enter the Krebs cycle after it does beta oxidation, which breaks down both even or odd chain fatty acids into acetyl-CoA units, which can then enter the Krebs cycle. Odd chain fatty acids end up doing some degree of gluconeogenesis as well. But there's a variety of fates that these metabolic substrates can have in the human body. But the take home is that we need fat and or carbohydrates to go along with our protein in our diet if we want to be metabolically healthy. My sense of this, which is really just kind of a back of the envelope calculation, is that you are going to need at least 10% of your calories from fat or carbohydrates, probably 20 to 30% of your calories from fat and or carbohydrates, or you are going to run into metabolic catastrophe with essentially rabbit starvation. Don't go here. And this is an interesting aside that I think with the extinction of megafauna, which is another question that Ben had, we have lost the large animals, and our ability to hunt large animals is really the determination of how much fat humans are going to get in our diet. As many of you may know, there are many theories about these mass extinctions that happened 13 to 14,000 years ago, around the time of the Younger Dryas period. I think every time I say Younger Dryas, everyone snickers. I don't think it's that funny. But anyway, Younger Dryas, there's hypotheses of a meteorite impact. This is the work of Randall Carlson, Graham Hancock. There are certainly people who are skeptical of this, but there is a lot of geologic evidence that there was a massive change in the structure of our Earth with major global environmental catastrophes 13 to 14,000 years ago. And there's pretty good anthropologic evidence there was mass extinction of about 75% of species on this planet. And in those extinctions were many species of megafauna that were very big and probably represented major fat sources for humans. So I think it's fair to say that in the last 14,000 years, humans may have had to rely more on carbohydrates because we either need to get fat or carbohydrates in addition to protein. If you go out in the woods, there's a lot of protein, provided you can get an animal, but there's many anthropologic, ethnographic, indigenous reports of people who hunt animals and they say there's no food here because the animals are too lean. Indigenous people know this. You need fat on the animal or carbohydrates. So one of the theses that I advance in my book is that plant foods are really fallback foods. If we cannot get fatty animals, we are going to have to look for carbohydrates as go-betweens. This doesn't mean they're necessarily bad for us all the time. I've been very vocal on my social media recently about drawing a distinction regarding the biochemical roots of insulin resistance, which I'll probably talk about in this podcast because it's super fascinating. I do not believe carbohydrates cause insulin resistance per se. There are many studies which corroborate that. I think that it's very clear that carbohydrates can fan the flames of insulin resistance in the setting of insulin resistance that is pre-existing, but they do not cause it de novo. So I'll get into that later. But this is a great segue to one of Ben's next questions, which is about the actual decline in human health that happened with the advent of agriculture. So Ben asks, is the decline in height and health fully attributable to plant agriculture, or could it be due to industrialization, crowded cities, etc.? And so I think this one is fairly easy to answer. There's a really good amount of evidence to suggest that this is certainly due to plant agriculture and the actual decline in the quality of the human diet. And the reason we can say this is because there was no industrialization, 12,000 years ago. There is Göbekli Tepe in Turkey, which looks to have been a major Neolithic site, but this is not industrialization. There are certain civilizations of people living in these places. But I think this ties in, at least hypothetically, to many of the concepts that Randall Carlson and Graham Hancock talk about. If there was indeed, and again, there's great geologic evidence here, I would encourage you all to listen to this series on Joe Rogan's podcast with Randall and Graham. There's great geologic evidence that there were massive floods and major extinctions 13,000 years ago. And some humans appear to have survived, clearly. But a lot of the species of animals that we were probably hunting went extinct. And I think this may have been one of the driving factors that spurred us to agriculture. Now, Jared Diamond has so eloquently coined this, the worst mistake in human history. And I think that there's good evidence for this to be true. In the book, I talk about surveys of humans at the Dixon Mounds, which are 10,000 years old. And you can actually see in the same archaeological sites over a 1,000-year period or 2,000-year period that the skeletons shrunk, the length of the femur and the humerus shrunk. There were many more lesions in the skulls, which is called porotic hyperostosis, spongiform change in the skull that we know is due to deficiencies of iron and other minerals. There are tuberculous lesions in the spine and long bones that become much more prevalent. There's evidence for poorly healed fractures. There's evidence for all sorts of really significant decline in human health. And they happen over, maybe 10 to 20 generations in a certain geographic area as the people there moved more toward farming. It makes sense that this was a decline in human health due to an absence of the nutrients that are so rich in animal foods. In chapter 8 of my book, I talk about the way that plants and animal foods compare in terms of nutrients and the fact that animal foods are really, in my opinion, and the opinion of many others, the best foods on the planet because they have all the nutrients humans need to thrive in the most bioavailable forms. Plants just do not have the nutrients that humans need. They really are fallback foods at best. Again, it's hard to go into details on all this. It's all in the book. Whenever I say that, though, people always say, what about vitamin C? And I'll just say a word about vitamin C quickly as an aside. There is vitamin C in animal foods. There is vitamin C in liver and spleen and organs. There's vitamin C in muscle meat. And a very small amount of vitamin C, on the order of 10 milligrams or less, is needed to prevent scurvy. I have not seen any convincing studies that in an otherwise metabolically healthy individual, we need massive amounts of vitamin C above what could be obtained by eating fresh animal foods on a daily basis to obtain optimal antioxidant status. So there are studies in hospitalized diabetics saying that 75 milligrams of vitamin C is better than 25 milligrams of vitamin C. But these are hospitalized people with tons of inflammation and insulin resistance. And we know that those with diabetes and insulin resistance do not utilize vitamin C as well. And for any given amount of vitamin C, they incorporate less of it into their cell membranes, into the aqueous layer, and utilize it worse. There's a study that I will talk about later in this podcast showing that when the amount of vitamin C in a diet was increased from 70 milligrams to 270 milligrams in an interventional group that included more fruits and vegetables in their diet, the serum levels of vitamin C went up 30%, but there was absolutely no change in their markers of inflammation, oxidative stress, or DNA damage. It's pretty darn easy to get 50 to 70 milligrams of vitamin C in an animal-based diet if that meat is not overcooked, if it's fresh, and if you're including organ meats and eating nose to tail. So you guys all know that nose to tail eating is hugely important for me. I love liver. Like I said in the intro to this podcast, Ben and I have eaten all sorts of organs, including testicle together. And I think this is a key part of the way that our ancestors used to eat organs that is left out. It's one of the reasons that I'm so passionate about helping people get these organs back into their diet. And I mean, this is really it's super exciting to be able to share with Ben's audience and my audience that I've developed my own line of desiccated organ supplements. So these are low temperature dehydrated Desiccated Organs. It's at Heart and Soil is my company. And the idea is, hey, if you can eat real organs, eat the raw organs or eat the cooked organs, eat the real thing. But many people don't have access to liver or spleen or pancreas or testicle or bone marrow or collagen in the right forms, which is why I am so excited to be able to provide this to people in a desiccated organ supplement. So that's the plug for my stuff, guys. You can go to heartandsoilsupplements.com to check out what we're doing there. And it's basically the idea is getting you guys back the nose to tail nutrition that we've always had before we became pastoralists and got much less healthy. This is how we reclaim our ancestral birthright to radical health. So check out heartandsoilsupplements.com. And my goodness, eat nose to tail. That is something you want to do for your health. Ben's next question is something that I actually addressed earlier. He says, why do you say present day hunter-gatherers no longer have access to large game? And it's basically what I was saying just then, that with this mass extinction event that happened 13,000 years ago, there are no woolly mammoth left on this planet. And they were twice the size of a normal elephant or more. Many of the indigenous groups that are currently living in the US, or I guess there are not many indigenous groups living in the US, I should say Africa or other regions of the world, can only access much smaller game. In the grand scheme of human evolution, a buffalo is probably one of the biggest things that humans hunt these days. Maybe in Africa, giraffe are able to be hunted depending on the laws, but elephants are essentially endangered, and I don't think many indigenous groups are allowed to hunt elephants. And so that's what I mean, that in the grand scheme of human evolution over the last 3 million years of hominid evolution, we were probably hunting very big animals, big, much bigger than a buffalo. And a buffalo is probably the biggest thing humans can hunt today in most places in the world. So that's what I mean when we don't have access to large game. And without access to large game, we don't have access to large amounts of fat anymore. This is probably a major driver for the amount of plant foods and carbohydrates in indigenous diets, that we are filling in that niche that is left by the biochemistry that I talked about with the urea cycle. We need carbohydrates if we can't get a lot of fat. So it's not surprising that many indigenous hunter-gatherer groups, if they can't hunt big animals, are sort of forced to gather more than they would have in the past. If you can get a lot of fat, you're going to be fine, and you're going to eat tons of fat. Now, again, I have no problem with carbohydrates. In the book, I have a tier 1 carnivore diet, which outlines the foods that I think are the least toxic. In my view, it's the fruit. It's the part of the plant that the plant actually wants you to eat. I think it's okay to eat carbohydrates if you are insulin sensitive and metabolically healthy. In the setting of metabolic dysfunction, low carbohydrate diets can be very helpful in the short term, but we must know what the main cause of insulin resistance is. I'll get to that later in this podcast, but I strongly believe it is polyunsaturated vegetable oils, specifically linoleic acid, causing the mitochondria in our visceral fat to become broken. And we know that that visceral fat, that fat inside of the peritoneum, is what determines the insulin sensitivity of the rest of the body, mostly by lipokine signals from that fat through the circulation to the peripheral muscles, brain, liver, all the tissues of our body. Even the immune cells can be insulin resistant in the setting of insulin resistance arising from that visceral fat. Again, that is a preview for what is coming later, but that is what I mean by humans no longer having access to large game. And I've talked about this on a previous podcast with Chris Kresser and Chris Masterjohn, that if you look at indigenous people, they are actually smaller than their relatives over a number of generations. And this is probably because they are limited in their scope. They're limited in their hunting lands. They're limited in what they can hunt. Indigenous people are unfortunately limited, whether it's the Hadza, the Kung, the San, whoever. They're limited by the countries they live in now. They're the minority when, that's shifted in the last, 300 years. So they're limited in what they can hunt legally, and that is affecting them in terms of their stature, in terms of their overall nutrient availability. They don't have access to big animals anymore. If they could go hunt elephants, it might be a different story, or if they could hunt giraffes, but they can't do that so much anymore if those species are endangered. That's what I mean by that. And hopefully that helps clarify and ties it into the fact that humans need fat to complement the protein and or carbohydrates, which can be eaten in a very helpful way. I just think that many of the carbohydrates that most are eating in mainstream society today are grain-based and full of many more toxins, which cause massive issues for humans, as I talk about in my book in more detail. So hopefully that ties it all in a bow there with regard to those questions. Also related to this topic of what humans have been eating and how we've been eating it for the last 3 million years is another question that Ben had, which I think is actually very insightful. He says, how do we know the reason our stomachs became 1,000 times more acidic than a chimp is because of animal food consumption? And there are some really good studies which address this that I talk about in the book. I will screen share one of these. There have been some really interesting analyses looking at different species, looking across birds, looking across humans, looking at chimps, looking at other animals. And what has been found consistently is that the pH of the stomach, meaning the amount of acid in the stomach with a lower pH indicative of more acidic or more protons in the concentration, is associated with phylogenetically distant foods, meaning they are more likely to eat foods that are distant than them and that are likely to be rotting. And this is something we see across species, and it's a pretty good indicator that human stomachs are very acidic on the order of 1 to 1.5, likely due to the fact that our first foods were carrion, were not carrion in the airplane, but carrion, C-A-R-R-I-O-N, meaning rotting animal flesh. I think as we became better hunters, we were able to get fresher and fresher meat, but I do believe that fermented meat and rotten meat has been a part of our diet for a long time because refrigeration has only been around for a very short amount of time. If any of you are familiar with the concept of high meat or high liver or high organs, you will know that it's totally possible for a human with a very acidic stomach to eat a completely, quote, rotten piece of meat and be just fine because we have a very acidic stomach. And the theory here is that this is because the very acidic stomach of our species and of other ancestors or of other animals that also do this prevents the sort of accumulation of foreign microbiota into our guts. It's a filter. And what we know is that our microbiome, we don't want that to be full of pathogenic organisms, so we're going to filter out the ones we don't want in the gut, in the stomach, and that happens with a very acidic gut. So here is the paper that I'm referring to. I reference this in the book, The Evolution of Stomach Acidity and Its Relevance of the Human Microbiome. Again, for those listening online, this will be on a video version if you want to see this paper. This is a group that did a really interesting review looking at the they wanted to test the hypothesis that the vertebrate stomach was there, and the pH of the vertebrate stomach was there to maintain the gut microbial community by filtering out novel microbial taxa before they pass into the intestines. Their hypothesis was that species feeding on either carrion or organisms that are close phylogenetic relatives should require the most restrictive filter, measured as a highly acidic stomach or a high stomach acidity. I don't love their verbiage here. A high stomach acidity means a very acidic stomach. I believe earlier I said they were distant phylogenetic relatives. I misspoke. They are saying these are close phylogenetic relatives, and they are feeding on carrion or organisms that are close phylogenetic relatives. They want to protect themselves from foreign microbes. Conversely, their hypothesis is that species feeding on a lower trophic level or food that is distantly related to them, herbivores, should require the least restrictive filter as the risk of pathogen exposure is lower. They found that comparison of stomach acidity across trophic groups in mammal and bird taxa show that scavengers and carnivores have significantly higher stomach acidities. Again, their verbiage here is very misleading. This means they have lower pH and more acidic stomachs compared to herbivores or carnivores feeding on phylogenetically distant prey such as insects or fish. In addition, we find when stomach acidity varies within species, either naturally with age or in treatments such as bariatric surgery, which is things like Roux-en-Y gastric bypass surgery, the effects on gut bacterial pathogens and communities are in line with our hypothesis that the stomach acts as an ecological filter. This is the main problem with proton pump inhibitors. Hopefully very few of you listening to this are taking proton pump inhibitors. I think that this is also why we should be very careful with bariatric surgeries like Roux-en-Y gastric bypass or gastrectomies that can affect the pH of the stomach, because that will essentially abrogate, that will remove the ability of our stomach with its lower pH to filter out the microbial communities we are getting. And as they are saying, there is good medical evidence that when we take proton pump inhibitors or even H2 blockers, which are the histamine blocking drugs, which also affect the pH of the stomach, that will affect the gut microbiome in a negative way, allowing organisms that should not be there to make their way through and leading to massively bad consequences. Many of you may also know that proton pump inhibitors are a big problem in terms of absorption of nutrients and lead to things like B12 deficiency. They've been associated with increased rates of dementia and community-acquired pneumonia for the reasons that are not surprising, because the stomach is not a filter anymore. You can get bacteria, and that bacteria can be aspirated into the lungs. B12 and many nutrients require an acidic stomach. Imagine that. 3 million years of evolution made this acidic stomach for a reason. When we get rid of it by treating a symptom rather than the cause, we have major problems. So the quick takeaway here is do not take a proton pump inhibitor without understanding the root cause of your gastrointestinal reflux disease. You do not overproduce acid. You are most likely refluxing because of dysbiosis and a loss of microbial diversity throughout your intestines, which is correctable by diet. So this is one of the main problems, these main bones I have to pick with Western medicine, is the massive use of proton pump inhibitors without any attention to the fact that gastrointestinal reflux disease is a preventable, treatable thing. Back to this paper, you can see that they go through many sort of explanations here which show this, and they come to this conclusion like I suggested in the abstract. They have a graph here looking at the acidity of our stomach versus other stomachs, whether they are obligate scavengers, facultative scavengers, generalist carnivores, omnivores, specialist carnivores, herbivores in the hindgut or the foregut. But the takeaway here is that looking at all of the pHs of these stomachs, their theory seems to hold up pretty well. I think that the answer to Ben's question here is there's a pretty darn good amount of literature to suggest that the pH of the human stomach is tightly tied to the fact that we have been eating animals for 3 million years, and probably the first animals we were eating were rotting, and that we can still do that and protect the consistency of the microbiota in our guts by keeping a very acidic stomach. We want that. It's said that we lose that acidic stomach as we age. I don't think that's a necessary thing that's connected with aging inextricably. I think it has to do with loss of nutrients as we age, development of insulin resistance as we age, and that is the main problem there. So in general, one of the messages that I talk about in the Carnivore Code is do not accept the excuse from your physician that you are sick just because you are getting old. That to me is baloney. Humans should be able to live well and thrive well into old age. We see this in indigenous hunter-gatherers, and we should not lose mental clarity, agility, strength, libido, or stomach acidity in the way that Western medicine accepts with this steady decline. This is what's called the squaring of the morbidity curve, and I've talked about it on previous podcasts with people like Bill Von Hippel on my podcast, which is Fundamental Health. And we see this in indigenous hunter-gatherers, that they retain many more of their faculties, their strength, libido, body composition, stomach acidity, freedom from chronic disease much later in their lives than modernized Westerners. So do not accept the notion that you are getting old. That is one of the most insidious, I think, ideas that is foisted upon us by Western medicine that needs to be challenged. So much of what we do, what Ben does, what I do, is about helping you stay as vital as possible, as long as possible, by understanding how to live. And most of it is just mirroring the way our ancestors lived. What's so interesting to me is that a lot of biohacking today is a mirroring of the way that our ancestors were living for 3 million years. And now we're trying to incorporate it into a 2020 paradigm. So moving on, Ben's next question is that on page 41, I say that herbivores can detoxify plant toxins, but we can't. How do they do it? So this is a really interesting point because Ben is very astute here. If plants are toxic, then why can some animals eat them? And if you look at the zoologic literature, what you quickly realize is that there are unique adaptations in many animals, specifically ruminants or even monogastrics like rabbits, etc., to these plant compounds. They have compounds in their saliva that detoxify them, that allow these compounds to become more volatile. There are compounds in moose saliva that actually detoxify and break down polyphenols like tannins, which act as digestive enzyme inhibitors if they pass through undigested. So this concept, the second thesis of the carnivore code, my ideas that I talk about in my book, is that plants exist on a toxicity spectrum. And I've talked about this in previous podcasts with Ben, but I'll just mention it here for a moment. And it's this idea that, look, plants are rooted in the ground. They have no defenses other than the chemicals they've developed. And there is an arms race that has been happening between plants and animals and insects and fungi for the last 450 million years. There is no debate that plants are full of toxins. The only question is, how good is any individual species of insect, animal, or human at detoxifying those toxins? There's no question that plants don't want to get eaten. Animals don't want to get eaten either, but they can cook, they can kick you, not cook, that's a Freudian slip. They can kick you, you can cook them respectfully after you've hunted them, but they can kick you, they can gore you, they can bite you, they can get you with their antlers, but plants can't run away. So we see that in humans, there's actually been this development of these detoxification systems in the liver. The CYP450 systems, phase 1 and phase 2 detoxification systems in the liver. But humans, I believe, are not as good at detoxifying plants because we haven't been eating them as the majority of our diet for the last 3 million years like an herbivore has. We've sort of lost this knowledge. I think that humans have a passing ability to detoxify plants, but if we overload that ability by eating one plant excessively or by stumbling upon a plant that this one individual is particularly bad at detoxifying, then we are going to have a major problem. And this is really what I'm talking about with the carnivore code. The goal is not to convince everyone to stop eating plants. Like I said, it's number one to really shout from the rooftops that red meat, animal foods, organ meats, like I talked about, are critically important for humans and should be a part of every human diet. And number two, that plants exist on a toxicity spectrum. And if you are not kicking all the ass you want to kick, you may not be detoxifying the toxins in that plant as well as you could be. And if you can get animal foods all the time, maybe you should consider making those a bigger part of your diet, because those are really the major superfoods where humans get the majority of their nutrients in the most bioavailable forms. So again, one of the theses that I advance in the carnivore code is that plant foods are fallback foods. And we see this in our ancestors. We see stable isotope studies of Neanderthal, coexistent Homo sapiens from 40 to 50,000 years ago, and stable isotope studies from 2 million years ago looking at teeth and bones, showing us that humans have been eating a lot of meat. We can look at these stable isotopes and get a sense of where our protein is coming from. I talk about this in the book as well. And we see that humans exist on a graph of trophic levels of eaters of food around the area of a high-level trophic carnivore, meaning that we had stable isotopes, nitrogen, sulfur, calcium, barium, and strontium in our bones and teeth that were mirroring or even higher than high-level trophic carnivores, things like hyenas, which we can compare them to. So it's suggesting that humans have been eating mostly meat or a lot of meat for a long time. It would make sense then that we wouldn't have as highly developed detoxification systems. Ruminant animals specifically can detoxify many plant toxins in the rumen, in the foregut. They have a lot of bacteria there that can detoxify these in a special way that humans don't have. And they, like I said, they have special enzymatic systems. Moose have things in their saliva. Rabbits and other animals are known to chew grass excessively with an open mouth to allow many of the toxic compounds to aerosolize. So this idea that we are just not that well adapted to eating plants, we don't have the ninja skills to detoxify these things like herbivores do, that's pretty well documented in the zoologic literature. There's a really interesting paper here that I'll share, the coevolution of poisonous plants and large herbivores on rangelands. And what they talk about in this study is that, that herbivores do have evolutionary adaptations, and these include a generalized diet that reduces the probability of eating a toxic amount of any one species, number one, I'll talk about that in a moment, the ability to detect and avoid poisonous plants, number two, humans are horrible at that, and the ability to detoxify plant poisons, all appear to operate, at least to a degree, in both domestic and wild herbivores. Now, what's interesting is that native big game animals are occasionally poisoned by plants, but large losses usually occur in overpopulated or overgrazed areas where non-poisonous species have been depleted. So it's possible, even for herbivores, if their environment has been so badly altered by overgrazing or by the confinement of them, that they can be forced to eat too many toxic plants. But I want to talk about those 3 points of this paper. The first one, they have a generalized diet that reduces the probability of eating a toxic amount of any one species. Humans eat essentially 12 species of plants that have just been hybridized to look like many different plants in the grocery store. We are eating the same plants over and over and over. And again, I think that the most toxic parts of plants are roots, stems, leaves, and seeds. I go over all this in my book. But we are eating the same roots, stems, leaves, and seeds over and over. If our ancestors were going to eat plants, they would have 10x, 100x the amount of variety of these plant foods, meaning even if they were eating plants, they would be much more likely to get a bigger variety. It's simply not possible for us to do this. And this may be one reason that so many people have problems with plants today. I think that the underlying ideas hold true that we don't need to eat plants as humans. But as a fallback food, I believe that no matter where on the earth we were living, what latitude or wherever, we would have had access to hundreds, if not thousands more varieties of plants, which made the probability of overwhelming our bodies with these toxins very different. Like I said earlier, there's not a question of whether plants have toxins. The question is whether any individual can adequately detoxify those. And the question I'll ask the listener is, why are you eating plants in the first place? Again, I'm not judging anyone. I want your quality of life to be the highest it can be. But if you're not thriving, is there a possibility that some of those plants are causing you problems? And are you thinking you're getting unique nutrients in those plants? Possibly, but my guess is that you could get those same nutrients or even more nutrients in more bioavailable forms in organ meats or eating more rich animal foods, more well-raised, grass-finished, regenerative animal foods. So there's this widely sort of held notion, which I believe is false, that plants are this unique magical source of nutrients. We can get into polyphenols. I've sort of given my perspective on that, why I don't believe polyphenols are uniquely valuable for humans in the past. But in terms of known vitamins and minerals, there are none that occur in plants that humans cannot get in higher amounts in animal foods. And animal foods have a number of, quote, zoonutrients that do not occur at all in plants. Creatine, carnitine, carnosine, choline, or in any appreciable quantity in plants. Vitamin K2, vitamin B12. What about the peptides? BPC 157 occurs in the stomach lining of animals. Thymosin alpha 1 occurs in the thymus. Liver has LEAP2, liver expressed antimicrobial peptide. Pancreas has pancreatic polypeptide. These peptides are bioactive in humans. We know this. They don't occur in plant species, So the notion is clear here. Animal foods are the ultimate foods for humans. If we want to eat plant foods for color, variety, texture, fine, but understand that you may not be great at detoxifying all those things. And I think for a lot of people, they are misled into believing that especially foods like leafy greens and nuts and seeds are good for them when in fact they are causing major, major problems because we're pretty bad at detoxifying these. And unlike herbivores, we don't eat a wide variety of a diet. We're eating the same thing. How many of you guys eat the same spinach salad 3 times a week? Or it's spinach and kale, and those are the only 2 leafy greens. Or it's spinach, kale, and arugula. That's not evolutionarily consistent. The toxins in those foods can absolutely build up, and you can only detoxify them to some extent. So it's not that you can never eat them. I don't think they're doing you any good, especially spinach, super high in oxalates, as I talk about in my book, I think is a nightmare for humans. Kale is a big problem because of the goitrogens, the isothiocyanates. I'm going to talk about that in a moment. But if you want to eat them, you would do well to eat them rarely and do a very big variety. That's the key. That's what we're not doing. We really can't do that as humans. We've lost the knowledge, and we don't have the amount of biodiversity around us to go hunt and gather these things anymore either. And then the last point there was that the animals do have an ability to detoxify things that's better than ours because they've co-evolved with them, and we just haven't. I just think we've lost it. We have a small passing ability to detoxify these plants with our phase 1, phase 2 detoxification. We know that some people are better than others. But as I talk about with Ben in the first episode that we did together, don't you dare eat pepper because the piperine in the pepper is going to inhibit UDP glucuronosyl transferase, which is just one of the phase 2 detoxification enzymes that allows you to put a glucuronide moiety on molecules like curcumin that your body does not want. Go back to that episode if you guys haven't heard me talk about that. It will blow your mind. All right, so that's a pretty good natural segue to talking about isothiocyanates. This is a controversial topic. These are molecules like sulforaphane and goitrin, which is another isothiocyanate that's very rarely talked about, but I'll talk about more today. So Ben asks, what are the studies of these in humans? And I want to show one. I think I actually mentioned this one in the book, but I want to highlight this one study because people actually say, Is there any evidence that these actually harm the thyroid gland of humans? And I think there is very good evidence that these isothiocyanates can affect the thyroid gland of humans negatively. They are goitrogens. They are big problems for humans by inhibiting the absorption of iodine at the level of the thyroid, and I think many other problems. If you don't believe me, then just look at rural Africa and the basically how many people there have endemic goiter, which are these huge thick necks. They are forced to eat many foods there, millet or cassava, which include goitrogens, and those foods inhibit the absorption of iodine. If you are eating a low iodine diet, like they may be, because they are not eating as many animal foods, they're eating mostly plant foods, and you are especially including a plant food diet that has many goitrogens, you are going to end up with hypertrophy of the thyroid, which is this endemic goiter, these really big thick necks. So there's definitely evidence that these are a big problem for humans. If you are eating animal foods, this is much less likely to happen, but could it be affecting your thyroid at a negative level, at a mild level, negatively? Absolutely. And I think this is why these foods should not be a part of our diet. The risk is absolutely not worth the benefit in any way, shape, or form, in my opinion. I think that's pretty darn clear. So why do I hate these things so much? The idea here is that isothiocyanates exist only in these brassica foods when they are chewed. It's a booby trap, meaning the precursor molecules, which are generally called glucosinolates. In the case of sulforaphane, it's glucoraphanin, which combines with the enzyme myrosinase. When you chew it, it makes sulforaphane. And similar with goitrin, it has a precursor molecule that combines with myrosinase to make goitrin. Both of these molecules have been found to significantly inhibit the uptake of iodine at the level of the thyroid, but goitrin and many other molecules like that are even more effective at this than sulforaphane. So this is a real problem. This is a booby trap that is waiting to be sprung, and the plant's intentions are clear here. They are trying to mess up our thyroids. I don't know why we persist in eating them. So I'll screen share this study, which I think is one of the best ones. The concentrations of thiocyanate and goitrin in human plasma, their precursor concentrations in brassica vegetables, and associated potential risk for hypothyroidism. And so you can see here, they say radioiodine uptake to the thyroid is inhibited by 194 micromole of goitrin, but not 77 micromole of goitrin. And it says here, collards, Brussels sprouts, and some Russian kale contain sufficient goitrin to potentially decrease iodine uptake by the thyroid. Now, this is exactly what I am talking about, you guys. Why are we eating these foods? The intention of these foods is very clear. There are no unique nutrients in these brassica foods for humans. We don't need these foods. I'm going to go on record and just say, as much as I appreciate Rhonda Patrick's work, I believe she is really, really wrong about this. Sulforaphane, goitrin, isothiocyanates are not part of a healthy human diet in any way, shape, or form. Trust me, your gut will thank you, your thyroid will thank you so much when you get rid of these foods. Why do we believe these foods to be beneficial in the first place? There are studies with sulforaphane showing that it can turn on the NRF2 system. And this will be another question that Ben has that we'll get to in a moment. But you can take sulforaphane, and sulforaphane is a pro-oxidant. It's so often been talked about as an antioxidant, but that is false. Biochemically speaking, that is inaccurate and false. Sulforaphane is a pro-oxidant, meaning it steals electrons from other molecules. Well, when it comes into our body, we try to detoxify it very quickly. The little bit that circulates goes around and steals electrons from other molecules, creating free radicals and activating antioxidant response elements in our DNA. These turn on multiple genes. You get this NRF2 keep 1 complex, which dissociates. Essentially, NRF2 moves to the nucleus as a transcription factor and turns on these ARE, these antioxidant response element genes. Now, these code for more enzymes that make more glutathione. Sounds like a great thing, right? Except it's a redundant benefit. We don't need that. There's no evidence that sulforaphane gives us extra glutathione or more glutathione than we would have if we were living optimally. This is the very important distinction that I want to draw between molecular hormesis and environmental hormesis. One of Ben's follow-up questions, which I will loop in here, is that on pages 48 through 50, I talk about something called the bad news gang, like cigarettes, alcohol, etc., that also turn on NRF2. So NRF2 is interesting. This is a transcription factor that is involved in hormesis in the human body. It can get turned on by many things. It can get turned on by cigarettes, alcohol, lead, mercury, sunlight, cold exposure, ketosis. And this is where I want to draw a very distinct, very important distinction that I make in the book. I've never heard anyone else talk about this, but I debated David Sinclair about this on my podcast, and I don't believe in his concept of xenohormesis, and I'll tell you why. There's a big difference between molecular hormesis and environmental hormesis. Environmental hormesis was what I did last night. I went to a sauna with friends, then I jumped in a cold tank. Those definitely turned on my NRF2 pathway. And I have more glutathione now, along with other enzymes, in that antioxidant system because of that, right? That is an environmental hormetic. There's no molecule circulating in my human body. I do get more oxidative stress, and that turns on molecular mechanisms. Sunlight, exercise, sauna, cold plunging, ketosis all do this, right? There's no exogenous molecule coming in. Molecular hormesis or xenohormesis, xeno is a prefix that means alien. That is when we introduce a molecule like sulforaphane into our body, or resveratrol, or curcumin, in the hopes that it will affect our biology. In this case, in the case of sulforaphane, it acts as an oxidative stressor and turns on NRF2. What is the difference here? It's an exogenous molecule that has side effects. I talked about this in the first and the second podcast that I did for Ben. These molecules are like any other molecule you will get at the pharmacy. They have side effects. This is a package insert. They are exogenous molecules that do not participate in any of the biochemistry of humans intrinsically. They are only introduced as foreign molecules. If you go to the pharmacy and get a prescription for metoprolol, lisinopril, or a statin drug, not that you would really want to do that, but if you did, they would give you a package insert which has all the side effects. All of these exogenous molecules like sulforaphane, curcumin, resveratrol also have a package insert, but we're never told about it because the supplement manufacturers want to sell these. Now, this is the problem I have here. Now, Ben may disagree with this. We will respectfully agree to disagree, but I so appreciate that he allows for this back and forth dialogue on his platform. The problem that I was illustrating with sulforaphane earlier is exactly this. Sulforaphane might increase your glutathione, but it's also going to circulate in your body along with goitrian and other isothiocyanates that are present in those brassica vegetables and wreak havoc on your thyroid and other hormonal tissues. That is not worth it. That is a side effect of the medication, quote medication, that is a side effect of these exogenous molecules that are participating in xenohormesis, that are acting as xenohormetics, that you don't get when you get environmental hormesis. So this is the really, really important answer to Ben's question. Environmental hormesis doesn't introduce side effects. Yes, environmental hormetics and xenohormetics can turn on NRF2. The difference is that molecular hormetics then circulate in the human body and have all sorts of negative side effects. And that is what is not worth it, because there are multiple studies to show that in humans who are living well, who are doing cold water plunging, eating nutrient-rich diets, that the addition of fruits and vegetables with these polyphenolic molecules or isothiocyanate molecules does not do anything to increase your antioxidant capacity. It's already optimal. And when I've done tests on myself and my clients, we don't have oxidative stress because we don't have polyphenols. I joke about this on my Instagram. Here I am, I have a polyphenol deficiency. Those of you who can't see me because you're listening should look at what I look like online. My skin is not melting off. I've shared these labs before. My 8-hydroxy-2-deoxyguanosine is normal. I don't have lipid peroxides that are elevated. My CRP is as low as it gets. I don't have oxidative stress, and I don't eat polyphenols from plants. I definitely don't eat isothiocyanates. And guess what? My thyroid works great. Thank you very much. So this is the nuance that I'm just trying to explain here, that you don't need these polyphenolic molecules, these isothiocyanate molecules, to be optimal from your antioxidant status, and you don't want the collateral side effects that come with them. The risks are not worth the benefits. These are risks with redundant benefits that you can achieve by eating a nutrient-rich diet and doing the environmental hormesis activities, sunlight, cold, sauna, exercise, all that stuff, ketosis occasionally. Ben and I will agree on all of that. So that is really what's different between the molecular hormesis and the environmental hormesis. And you can see the environmental hormesis is not a molecule. It's not going to circulate. It's not going to do many negative things. I talk about resveratrol in the book. I talk about curcumin in the book. And I go into details about the dark side of these molecules. And I talk about many studies that show how many bad side effects these molecules can have in humans. In the case of curcumin, it's known to inhibit topoisomerase enzymes, which wind and unwind DNA. It can affect P53, which is a tumor suppressor gene, in a negative fashion. It affects the hERG channel, which is a potassium channel. And it's been found to be both toxic to both native and cancerous cells in cell culture, as well as other problematic things in humans. Resveratrol decreases androgen precursors in humans. Not a very good thing. I'm going to talk more about resveratrol in detail later in this podcast. You do not want your androgen precursors to be lowered, which is your DHEA and your testosterone, by taking a xenoestrogen like resveratrol for a redundant effect. In the case of resveratrol, you can definitely turn on your sirtuins by fasting and ketosis. I did a whole podcast with David Sinclair, and he was actually surprised. He's a brilliant guy, but he just wasn't aware of ketosis. And in that podcast, which you can hear on my show, I showed him studies, and he agreed that there are many studies which show that when you're in ketosis or fasting, your NAD to NADH ratio changes positively, and you turn on sirtuin genes. As I'll talk about at the end of this podcast, when I talk about what I eat, I think we should cycle in and out of ketosis. I don't think we should be in ketosis all the time, but occasional ketosis or intermittent fasting can absolutely turn on your sirtuin genes. Like I said, these are not unique effects of these molecules. Xenohormesis is a flawed philosophical concept that is conflated ideas or benefits from environmental hormesis, when in fact, you can be optimal by living a radical life, quote unquote, which is what I say in my book, by just sunlight, heat, cold stress, exercise, and fasting occasionally. Hope that makes sense, and it ties together a number of concepts. I'm glad those came together like that. To really drive this point home, I want to share a couple of studies. There are many more like this noted in the book, and I want to show how the inclusion of larger amounts of fruits and vegetables into a diet had no effect, no beneficial effect on antioxidant status or any of these other things. And this is going to be the study that I mentioned earlier with regard to vitamin C as well. So again, there are multiple studies like this that I reference in the book. Ben asks about these from the context of the length of time. This is a 12-week study, which is actually a pretty long study when it comes to these type of studies. So let's dig into this one, and I will show you what it looks like. So this one is called The Effect of Increasing Fruit and Vegetable Intake by Dietary Intervention on Nutritional Biomarkers and Attitudes to Dietary Change, a randomized trial. This one is super interesting. So this is a group of 19 men and 26 women with a low reported fruit, juice, and vegetable intake, less than 3 portions a day. They were randomized to consume either their usual diet with small amounts of those in their diet, or a diet supplemented with an additional 480 grams of fruit and vegetables and fruit juice for 12 weeks. They looked at nutritional biomarkers, vitamin C, carotenoids, B vitamins, antioxidant capacity, and genomic stability pre-intervention and at 4, 8, and 12 weeks. They also looked at glucose, homocysteine, lipids, blood pressure, weight, arterial stiffness, and they assessed the intake of fruit juice, vegetables by a questionnaire over the course of the study. This is an interventional study. This is not observational epidemiology, which makes it so powerful. Again, this is just the abstract. If you guys want to read the whole paper, it will be linked in the show notes, as is everything else I am showing you here. They said the intake increased significantly. The plasma vitamin C went up 35%, as did the carotenoids, which is not surprising, and we can talk about why that might not be a very good thing in a moment. But there were no significant changes in antioxidant capacity, DNA damage markers, or markers of vascular health. Isn't that interesting? Why do we believe that fruits and vegetables are so magical for us when over 12 weeks, this is essentially almost 3 months, you guys, how much longer do we need to see a benefit? There is no change in these markers of genomic stability, antioxidant capacity, vascular health with these. And as they say, the vitamin C level in the plasma went up 35%, and there was no change in the antioxidant capacity. If you really dig into the paper, what you will see with this one is that before they had the intervention, they were eating about 70 milligrams of vitamin C per day, as I said earlier. And with the intervention, they had 270 milligrams of vitamin C, no change in any of those markers. Also, these fruits and vegetables were not like weenie fruits and vegetables. They talk about them in the paper. They're things like broccoli and cauliflower, Jerusalem artichoke, tomatoes, whatever. And they didn't change any of these things. So the problem here is then that there's really not a consistent level of evidence to show that these fruit and vegetables are valuable for humans. What's also interesting about these studies is that this is not a carnivore diet. This is people eating things like bread and cake in addition to their no fruits and vegetables. We can make this study even better by comparing a carnivore diet group or an animal-based group or carnivore-ish group to a group with many fruits and vegetables and really seeing the difference, because the people who were not eating fruits and vegetables didn't necessarily have an amazing diet either. It could have even been more pronounced. And in fact, there's one study that I'll show that illustrates this, that sometimes in these interventional studies, and I believe this next one was also 10 or 12 weeks, when we increase fruit and vegetables or when we remove fruit and vegetables, as happens in this next study, markers of antioxidant status get better. So let's look at one more study which illustrates this. The title is a little confusing, but if you read the study, it'll make sense. The title is Green Tea Extract Only Affects Markers of Oxidative Stress Postprandially, Long-Lasting Antioxidant Effect of a Flavonoid-Free Diet. What is this talking about? Basically, they were looking to see what the effects of green tea extract, green tea flavonoids and catechins were in the diet. And so they had one group of people who had no flavonoids in their diet. And basically the conclusion is here. They say the overall effect of the 10-week period without dietary fruits and vegetables, because in order to remove flavonoids and catechins, they had one group remove dietary fruits and vegetables. So I'll read this again. The overall effect of the 10-week period without dietary fruits and vegetables, ready for it, was a decrease in oxidative damage to DNA, blood proteins, and plasma lipids, concomitantly with marked changes in antioxidant defense. This is really striking, you guys. This is the kind of stuff that's never talked about, but is absolutely present in the literature and absolutely something I talk about in my book. They looked at things like 8-hydroxy-2-deoxyguanosine. They looked at things like CRP. They looked at other markers of oxidative stress, hemoglobin protein oxidation, plasma oxidation, activities of erythrocyte superoxide dismutase, glutathione peroxidase, glutathione reductase, and catalase. They looked at all these measures. They got better when fruit and vegetables were removed. So again, this is what I'm beginning to say here, guys. Plant foods are survival foods. They're not an integral part of the human diet. They're going to provide you with molecular hormetics that may have a benefit if you look myopically at one small research study, but if you expand the lens, they can have negative effects. And there are even studies to show that fruit and vegetable depletion improves markers of antioxidant status. So this is really striking stuff. Just to drive this point home one more bit, I want to share the other two studies I was referencing earlier. This is a study looking at glutathione concentrations in cold water swimmers in Berlin. And it shows that by cold water exposure, you can have a decline in glutathione with an upregulation in your levels and increased in the next day. This is the control group. This is the group that is cold water swimmers. You can see their glutathione both reduced and oxidized. GSH is reduced. GSSG is oxidized glutathione. The interventional group, which does cold water swimming, has baseline levels of reduced glutathione that are significantly higher than the control group. And then after 60 minutes of swimming, you see both of those decline, and then they come back to higher than baseline. So this is the idea. This is environmental hormesis, guys. If you do cold water exposure, you can have higher levels of baseline glutathione, and that is what we want without any of the side effects associated with these molecules. We don't want molecular hormesis, in my opinion. You want environmental hormesis. Just one more. This is done in C. elegans, but you guys will love this. Hormetic heat stress and heat shock factor 1 induce autophagy to improve survival and proteostasis in C. elegans. There are similar mechanisms found in humans, just showing that if you do heat stress and you get this HSF1, this heat shock factor 1, that you do get autophagy, you do get this hormesis from the environment without molecules. There are no side effects to this one. We're going to induce the same mechanisms around NRF2, these antioxidant response elements, KEAP1, but there's no xenohormetic, there's no xenoestrogenic, there's no xenobiotic molecule, there's no foreign molecule in the human body that circulates and has all those side effects that I was talking about. So that is a hugely important thing. And as I was showing with those fruit and vegetable depletion studies, it's been shown repeatedly, not only that lower levels of vitamin C are probably fine and increasing it a ton doesn't make a difference, but both when you increase the amount of fruits and vegetables in the diet and if you completely eliminate them, it's not really going to change your antioxidant status much. And in that one study, we saw the elimination of fruit and vegetables led to an improvement in antioxidant status. So the paradigm needs to shift here. Animal foods are the foods that are nutrient rich for humans. Plant foods are survival foods. We can detoxify some of them, but not all of them. Be careful with them, and don't really believe, without doing your own research, which is I'm hoping to provide you guys with in the book, that you absolutely need these plant foods or any of these molecules in plant foods to be ideal. Okay, so Ben's next question has to do with isoflavones and chaga, which is a mushroom. There are two questions, but he asks the very good question, what about dose? And what do we know about dosing in these? The reason I get worried about isoflavones, things like genistein, and I believe the other one is diazyine, is that these are polyphenolic molecules occurring in soy that have been shown to have estrogenic effects in humans, which is not a good thing. They are xenoestrogens. And Ben says, well, what's the dose? What do we know about the dose? And so there are a number of studies which show that these are very estrogenic molecules. And there has been some concern about these for quite some time. I talk about this in the book, but in answer to Ben's question, I say that I would say that even moderate intakes of isoflavones from soy can cause pretty significant endocrine disruption. And I will show some studies which corroborate that, and I note a number in the book as well. So the first study is titled Goitrogenic and Estrogenic Activity of Soy Isoflavones. And this is addressing something that I talked about earlier with regard to isothiocyanates. So soy isoflavones are not even only bad when it comes to disrupting both androgens and estrogens, but they also have goitrogenic activity. So in this review, they do discuss the evidence for binding of isoflavones to the 17-beta estradiol receptor. This is not debated. And they show in vivo, so in the human body and in the body of rat studies, there is evidence for estrogenicity and developmental toxicity at levels that are found in the human diet. So genistein is the major soy isoflavone. It's also found to have a frankly estrogenic effect in women. And they look at observational studies in animal and humans suggesting a link between soy consumption and goiter, which is an activity independent of estrogenicity. This is iodine deficiency, which greatly increases soy's anti-thyroid effects. They say iodine supplementation is protective, but again, the intention of plants is very clear here. This is plant survival mechanisms. Plants do not want to get eaten. These are not your friends in any way, shape, or form. So this is showing at levels found in the diets of humans and in animal studies, soy isoflavones, pretty problematic in both of those regards. You're welcome to look into this in more detail if you want more details there. There's that study. There's also this study, which looks at the absorption of these chemicals in the human body, isoflavones, estrogenic activity, biological effect, and bioavailability. This is from the journal, European Journal of Drug Metabolism and Pharmacokinetics. And in this paper, you will see that just in the abstract, they say these are phytoestrogens with potent estrogenic activity. Genistein, diazyine, glycine are the most active isoflavones found in soybeans. There are many problems with soybeans, not the least of which is isoflavones. Later in this podcast, which is now getting to be pretty long and already in depth, we will talk about the other problems with soybean oil, specifically linoleic acid and polyunsaturated fatty acid. In this paper, they show these isoflavones, which do mimic estrogen. They look a lot like estrogen visually, and they show that they are easily absorbed. You can see they are easily absorbed, showing up in the plasma of humans with consumption. This is genistein. This is diazyine. And you can see that these really do affect human plasma levels when we eat them, and they are known to bind these receptors and cause both estrogenic and antithyroidal effects at normal doses. Just one more here. This is actually looking at the CA1 neurons in rats, but they show that even low doses in rats were able to affect the synaptic spine density of the hippocampus. Now, they sort of think of this as positive. I get a little bit worried about this. I think that a plant compound should not be affecting the way that synapses are forming in humans or animals. This is done on animals, and the reason I show the study is just that even low amounts of these low dietary soy isoflavonoids can change the way that neurons are being connected in rats. Again, it's an animal study, but it speaks to the dose effect to some degree. So in answer to Ben's question, there's pretty good evidence that even a moderate doses found in diets, soy isoflavones, which are a polyphenolic molecule, can mimic estrogen and do many bad things, including anti-thyroid effects similar to the isothiocyanates we were talking about earlier. These are not good foods for humans, you guys. These are survival foods at best. The other thing that Ben asks about is chaga. I share this study in the book, this chaga-induced oxalate nephropathy. And it's a case of a 72-year-old Japanese woman diagnosed with liver cancer. And she'd been eating a lot of chaga mushroom powder, 4 to 5 teaspoons a day, for the last 6 months for liver cancer. And she got oxalate crystal nephropathy. This is the first case report of oxalate nephropathy associated with ingestion of chaga mushrooms. The takeaway here is just that mushrooms are not benign either, and I have pretty significant concerns about the amount of oxalates in many mushrooms, including chaga. 4 to 5 tablespoons of mushrooms sounds like a lot, but there's a lot of companies out there now that are increasing our consumption of these, quote, medicinal mushrooms. I'm not convinced that they're necessarily beneficial or that they add anything to the human biology. They still want to defend themselves. They are still rooted in the ground, and we should be very careful with these. Personally, at an anecdotal, admittedly level, I had a really severe eczema flare right before I started the carnivore diet when I was doing multiple tablespoons of reishi, chaga, lion's mane every day, and I think this was a real trigger for my immune system as well. So mushrooms are not necessarily benign either, and they have oxalates, which I have a whole chapter on in the book, among other problems in mushrooms. So I'm not convinced that they're benign for humans either. They don't want to get eaten, and I think we should not be myopic like we have been with plant compounds and ignore the fact that many of the compounds in mushrooms that we think are beneficial could also have these side effects throughout the human body. They're probably not great for humans and probably would have only been used as survival food. Some of us might be able to detoxify them in moderate amounts, but are they really adding anything nutritionally to our diets? I'm not convinced. There are certainly case reports of them being harmful like the chaga. It's a high dose, but who knows? Certainly they seem to cause a problem for me, and these mushroom powders are making it easier and easier to get lots of these mushroom extracts in our diets. We should be careful of this. The next thing Ben asks about is resveratrol. If you guys are interested in this compound, which I mentioned earlier, it is a polyphenolic compound that does appear to activate sirtuins. I did a whole interview with David Sinclair. Mostly we talked about NAD, but resveratrol is involved in this as well because resveratrol and NAD are all connected with sirtuins. But the research is also pretty clear here. I want to show a few things which really make this crystal clear. I note a lot of studies in the book, which is why Ben raises this question, because these are not commonly talked about. I know David personally, he's a great guy, but I'm not convinced that this compound is good for humans in any way, shape, or form. The nuance here is that a lot of David's research is in mice. David is primarily a mouse researcher. He doesn't do clinical trials on humans. He's not a doctor, he's a PhD. So if you look at the actual research that he has done on PubMed or something, what you will quickly find is that these are mouse studies that David has done, and in humans, resveratrol does not look good at all. So let's make this very clear. So I'll screen share PubMed, David Sinclair, resveratrol. I'll show this study, resveratrol improves vascular function, but not glucose metabolism in older adults. And I'll show you a study showing that resveratrol actually worsens glucose metabolism. Here's a study. Resveratrol accelerates erythroid maturation by activation of FOXO3, ameliorates anemia in beta thalassemia mice. This is a mouse study. This is a mouse study. This is a mouse study. This is a honeybee study. This is a mouse study as well. Here's another mouse study and another mouse study. So this is the famous one by David Sinclair, that resveratrol improves health and survival of mice on a high-calorie diet. But again, these are all mouse studies. And when actually looked at in humans, resveratrol does not look like a good molecule, and I will show you why. So here's one. Resveratrol reduces the levels of circulating androgen precursors, but has no effect on testosterone, DHT, PSA levels, or prostate volume. Well, you don't want to decrease the levels of circulating androgen in humans. They were doing this to see if it would improve prostate outcomes, and it doesn't. but it will decrease your DHA and DHEAF, well, and androstenedione. This is not a good thing. You do not want resveratrol to decrease your hormonal precursors. That's going to decrease your androgens. Bad news. Just like other xenoestrogens like flavonoids, we don't want this to happen. And like I've said earlier, the benefits of resveratrol are probably mediated by sirtuins, and we can get these by fasting and ketosis in other ways. It's redundant benefit with these molecular side effects that are never accounted for or rarely accounted for. These are the package inserts that I get worried about. So next study, this is a placebo-controlled, randomized clinical trial, high-dose resveratrol treatment for treatment of non-alcoholic fatty liver disease. And what do they show? They show that in this placebo-controlled, high-dose, long-term study, resveratrol treatment had no consistent therapeutic effect in alleviating clinical or histological NAFLD, and they found that it actually worsened markers of metabolic syndrome. It says resveratrol treatment was not associated with improvements in insulin sensitivity or markers of the metabolic syndrome. In fact, it worsened them in this study and others. So that's another failure for resveratrol in humans. Strike two, sadly. And yet again, I have concerns about this molecule in terms of the way that it may cause even damage to DNA. So let's look at this study. Resveratrol, this is pro-oxidant activity of resveratrol in the presence of copper ions, mutagenicity in plasmid DNA. So it does improve, it does worsen DNA damage. So resveratrol alone resulted in deletion of mainly guanine bases. Our results suggest stabilization of such endogenous copper by resveratrol, resulting in pro-oxidant DNA cleavage at the site. And so this is not a good thing if resveratrol is even worsening potentially the mutagenicity, worsening the breakage of DNA. This is something I talk about a lot in my book, the ability of many of these compounds to cause clastogenesis, which is the breaking of DNA. So if you really look at the research here, resveratrol failed in human trials. There are not a lot of good trials in humans that show that resveratrol has a beneficial effect. It did improve diabetic mice, but then again, it's pretty easy to not to be a diabetic human. And I will talk about at the end of this podcast how to avoid being a diabetic human. So it's mostly mouse studies that have shown promise for this molecule, and then it fails in humans. But nobody ever talks about this, and it's still a multi-million-dollar industry. And the benefits are redundant. You don't need resveratrol to turn on your sirtuins. You don't want these side effects. Here's an observational study that's interesting. Resveratrol levels in all-cause mortality in older community-dwelling adults. And they found that in older community-dwelling adults this is in Italy, total urinary resveratrol metabolite concentration was not associated with inflammatory markers, cardiovascular disease, or cancer, or predictive of all-cause mortality, meaning it didn't do anything good. Resveratrol levels achieved with Western diet did not have a substantial influence on health status and mortality risk of the population in this study. Oh, well, that's a bummer. We all wish this were going to happen, but it just doesn't seem to hold up. And as we know, if you do super high doses of resveratrol, as you're trying to do in clinical studies, or if you do a supplement, it can have those other negative effects I mentioned, including worsening of metabolic function and decreased androgen precursors. I will show the one study that I mentioned in the search results on PubMed. I do believe David is an author here. It improves vascular function, mitochondrial number, but not glucose metabolism. And in fact, in other studies, it worsens glucose metabolism. Randomized, double-blind, placebo-controlled, N equals 30, 2 to 3 grams daily of resveratrol for 6 weeks. No improvements in glucose metabolism or insulin sensitivity. May have beneficial effects on vascular function, not clear. No beneficial effects on glucose metabolism or insulin sensitivity. You can get improvements in vascular function just by leading a radical life, like I talked about earlier. Why do we want all of the other side effects? There were no changes in glucose tolerance, insulin sensitivity, weight, blood pressure, or lipid profile following resveratrol treatment. That looks like a failed study to me in humans. So, unfortunately, resveratrol does not live up to the hype, and I believe often comes with many bad side effects. One of the next questions Ben asks is about probably one of the more favorite studies I have from the book that I'll show here. This is really interesting. It's on page 133 in the book. I talk about this study, food processing and emotion regulation in vegetarians and omnivores, an event-related potential investigation. Ben asks, what are event-related potentials and how do you measure them? These are essentially the way that we use electroencephalograms. We use EEGs in patients, and we can look at different amplitudes throughout the brain of the way that neurons are firing and to get a sense of how the body is reacting both consciously and subconsciously to different foods. What's so fascinating is they compared 24 vegetarians and 21 omnivores, and they had them either passively look at pictures of food that was meat and fish or that were vegetables. So they had them look at pictures, watch, or to change the appetite value of food. So they showed basically vegetarians and omnivores pictures of meat, and they looked to see what their response was. And you can look at different regions of the EEG, the P300 and the LPP amplitudes. And what you find is that in vegetarians, the aversions toward non-vegetarian food, that is meat, it prevails at the subjective level, kind of the cognitive bias level, and is consistent with their personal beliefs, meaning that vegetarians have an awareness, a cognitive, subjective, conscious aversion to food that is based on their cognitive bias. But at the neural level, the intrinsic motivational salience or relevance of meat is preserved, meaning that even in vegetarians who think that they don't like meat, their brain can't lie. And at a deep level in the brain, they still respond positively to meat. If this is not indisputable proof that we have evolved eating meat and that humans are meant and hardwired to eat meat, I don't know what is. If you really want to get into the details here, I'll show you how the EEGs look. Again, it's 11 sites on the skull. It's pretty complicated, but you can see these amplitude measurements. You can see the regions of the EEG at the bottom here. These are the grand average ERPs, the event-related potentials, from the front and central midline electrodes for two types of food stimuli. You can see vegetarian food, non-vegetarian food, and you can see how the changes were here. You can see other waves on the EEG, the P300, the slow wave, further graphs. These are the grand average ERPs at the central and right parietal. So the parietal, right electrodes for three emotional regulation conditions: watch, increase, decrease. And basically what you find, as I said, was that the salience, the relevance, the relative importance of these foods was maintained even in people who had a subjective or conscious awareness that they were averse to those foods. So you just can't erase from the human brain that these foods are very valuable for humans. This is super fascinating to me, and I think that it speaks to our evolutionary history with meat, as I've been saying throughout this podcast. All right, I know we've covered a lot of ground so far. Ben's got a couple more good questions I want to cover before we wrap this one up. This next one is actually some of my most favorite stuff that I'm talking about right now in my social media. It's been a fascination for me. So Ben says, if you say that carbohydrates that accompany plant fiber can spike insulin, that's painting with a pretty broad brush, isn't it? I think the lion's share of plants don't result in an appreciable insulin spike. So this is a great constructive criticism from Ben. I wish I'd clarified this a little more in the book. I do not think that an insulin spike is bad. As I said, and I hinted at earlier, I want to talk about insulin resistance and what causes it and what doesn't cause it. I do not think carbohydrates cause insulin resistance. And really the point that I was driving at in the book and could have done a better job at was saying that in the setting of insulin resistance, carbohydrates fan the flames. But I think it's polyunsaturated fatty acids, specifically linoleic acid, that really cause insulin resistance by increasing visceral fat. I'll show a couple of studies that talk about this. This is a whole podcast on its own. I have a number of resources both on my podcast, on my social media, talking about dietary stearic acid, which is a saturated fat, versus linoleic acid, which is, I think, is the main polyunsaturated omega-6 fatty acid that is causing the body to receive an environmental signal that winter is coming. And I will talk about this, and that makes us fat and insulin resistant. But really, the key here is that carbohydrates plus fat make us fat when that fat is polyunsaturated fatty acid. Carbohydrates plus stearic acid or plus saturated fat do not make humans fat. I believe there's really good evidence this is an evolutionary adaptation to winter, that when winter is coming, humans would eat nuts. And the combination of linoleic acid in those nuts and carbohydrates is a signal to the visceral adipose tissue to grow and for humans to become insulin resistant. We see this pattern over and over. It's really not controversial that combining vegetable oils, which are high in linoleic acid, with carbohydrates will make humans insulin resistant. What's fascinating is that stearic acid, an 18-carbon saturated fatty acid found in the highest concentrations in, wait for it, beef kidney fat, also known as suet, make humans insulin sensitive. This is one of the reasons that at Heart and Soil we wanted to make this supplement called Firestarter, which is a high stearic acid suet made into tallow oil. So again, heartandsoilsupplements.com, you can check that one out. It's actually tallow from suet. It's high stearic acid oil in a pill to give your body the signal that winter is not coming, to shrink the visceral adipose tissue, and I'll explain to you why that works. But you can also eat just pure beef suet, but it's much easier for people to get it in a pill in this tallow form, this rendered kidney fat form. Regardless, there's a real dichotomy between the way that stearic acid works in humans and linoleic acid work in humans, and even oleic acid. This is some concern about monounsaturated fatty acids. There's a big rabbit hole here involving the way that these fatty acids undergo beta oxidation in the mitochondria and the ratio of NADH to FADH2. And that ratio may be a key determining factor in whether mitochondria turn off or turn on. When mitochondria turn off, essentially what I'm saying here is that there are so many reactive oxygen species produced in that mitochondria because of reverse electron transport, that those reactive oxygen species send a signal to the insulin receptor to become insulin resistant. And generally speaking, when a mitochondria has more reactive oxygen species, it becomes insulin resistant. Again, there's a lot of nuance here, but the fats that we eat can determine whether our mitochondria become insulin resistant or insulin sensitive, meaning whether they burn fat or whether they shut off completely to the actions of insulin. So this is pretty interesting stuff. Again, it's a deep rabbit hole. I don't have time to go into it here, but I will show you some studies which illustrate this greatly. My point with the carbohydrates is that in people who are insulin resistant, the elimination of carbohydrates from plants can be very powerful because it removes the insulin signal. If you are insulin resistant, you don't want an extra insulin signal. So part of the problem with insulin resistance is that there is excess insulin signaling, and you don't want to be pushing that higher when you have high carbohydrates. Again, it's a temporizing measure. We have to correct the underlying issue, which is excess polyunsaturated fatty acids. At a high level, this has to do with the visceral adipose tissue. The insulin sensitivity of the visceral adipose tissue is what determines the insulin sensitivity of the rest of the body. What's tricky here is that they appear to be different, right? So you actually want your visceral adipose tissue to be insulin resistant. If your adipocytes are insulin sensitive, then when they see insulin from carbohydrates or anything you're eating, they are going to grow. We know that insulin is generally an anabolic hormone. When insulin binds to its receptor on adipocytes, you get you get lipoprotein lipase activated, which pulls chylomicrons out of the circulation, and they take up the contents of chylomicrons, which are fats, triglycerides. When insulin signaling is low, you get hormone-sensitive lipase activated in adipocytes, and there is fatty acid breakdown in adipocytes. So you want your visceral adipose tissue, which is actually an endocrine organ that we never really talk about. You want that part of your body to be insulin resistant because you don't want your visceral adipose tissue to grow. How do you make your visceral adipose tissue insulin resistant? You eat stearic acid, and I'll show you studies which illustrate this. If you want your visceral adipose tissue to grow, you feed it polyunsaturated fatty acids. This is what happens when winter is coming. When we're eating nuts, polyunsaturated vegetable oils, and carbohydrates, we get fat, and then the visceral adipose tissue, when that is insulin sensitive, it grows too big and it tells the rest of the body to be insulin resistant. This is a problem. So that's really high level. It's pretty complicated, but it's a very interesting idea. think about combinations of food in nature that are high in linoleic acid and carbohydrates. Not many: seeds, nuts, and breast milk. How do babies look? Really fat. There are times in our life for survival that we actually want to be somewhat insulin resistant. And the reason babies are fat and healthy is hypothetically, is possibly a big player here is the combination of polyunsaturated vegetable oils. Breast milk is about 12 to 14% linoleic acid and carbohydrates. When you push linoleic acid in your diet that high, I believe humans become insulin resistant. And this is the main problem. And it's a lipokine signal more than it's an oxidative stress signal at a broad strokes level. Let me show you a couple studies to illustrate this. I think it'll make it more clear. But the takeaway here is that carbohydrates are not the cause of insulin resistance. It is the underlying excess of omega-6 fatty acids, which are an evolutionary inconsistency in today's diet. We should have really only had those at 2 to 3% of our diet. And when we exceed that, we become insulin resistant by having visceral adipose tissue, which remains insulin sensitive and grows and then signals to the rest of the body to become insulin resistant. So check out these studies. The first one is actually done in rats, but it's really striking. So this one is really interesting. This is dietary stearic acid leading to a reduction in visceral adipose tissue in athymic nude mice. And this is, again, that's the third time I've said it because I think it's totally fascinating. It's really interesting. So visceral fat was reduced by 70% in the stearic acid fed group compared to the other diets. The lean body mass was increased in the stearic acid fed group compared to all other groups by DEXA. And they compared stearic acid to oleic acid and linoleic acid. So this is monounsaturated fatty acid. It's an 18-carbon monounsaturated, and linoleic acid, an 18-carbon polyunsaturated fatty acid. And unlike those, stearic acid induced apoptosis, programmed cell death, and cytotoxicity in preadipocytes in the visceral adipose tissue. What we're saying here is that in athymic nude mice, which is an interesting model, not humans, but I can show you studies in humans that show the same thing, stearic acid, which is predominantly found in cacao butter and suet from animals, reduced visceral adipose tissue in mice. There's an incredibly cool graphic here, which actually shows the visceral adipose tissue. You can see how small it is here in the mice. The corn oil, which is high in linoleic acid, much more. Even the safflower oil increased visceral adipose tissue. So I cannot say that we are convinced that monounsaturated fat is great for the visceral adipose tissue either. There's not a lot of monounsaturated fat in our diets, although there's a whole lot more of that than linoleic. And I think that if you're eating ruminants, you're getting monounsaturated fat. So it's probably not a big deal. I think the main signal here is linoleic acid and the combination of linoleic acid and oleic acid in safflower oil, or the fact that safflower oil still has way too much linoleic acid is what's causing this visceral adipose tissue to grow. But look at how much smaller it is over here in the stearic acid group. You can see here they actually measured the abdominal fat weight in grams. Stearic acid, much lower. Corn oil, safflower oil, much, much higher amounts of these. Stearic acid really reduced these, and you got, basically these mice got a six-pack when they ate stearic acid. You say, okay, Paul, it's in mice. Is that really true? I think it's pretty fascinating. Here's a study in humans. So dietary stearic acid regulates mitochondria in vivo in humans. So this is basically as good as it gets. What's so fascinating about this study is it took people and they put them on a low-fat vegan diet for 2 days. And they saw the amount of stearic acid in their blood drop precipitously. And they also saw mitochondria become fractionated, so segmented, and turn off. Then they gave them a milkshake with 26 grams of stearic acid, which is quite a bit, and the mitochondria turned right on and did fatty acid beta oxidation. They started metabolizing fat, and you see a drop in acylcarnitines, which are precursors for fatty acid beta oxidation. That's how we get fats into mitochondria, as we make acylcarnitines. So if these are dropping, they're going into the mitochondria where we're doing fatty acid beta oxidation. So they say, we show here that ingestion of C18, stearic acid, rapidly and then robustly causes mitochondrial fusion in people after 3 hours, causes a drop in circulating long-chain acylcarnitines, suggesting increased fatty acid beta oxidation in vivo. This work thereby identifies stearic acid as a dietary metabolite that is sensed by our bodies to control our mitochondria. Fascinating stuff. All fat is not created equal. All calories are certainly not created equal. It's a little hard to see. You guys can see this on the video if you're watching. You can see the mitochondria here are merged in this graphic. You go from fragmented mitochondria, which are here in red, to merging mitochondria here when you give them stearic acid. So they have a mitochondrial stain. You can also see the nucleus stains are changing, but there's actual changes in mitochondrial activity when you give humans lots of stearic acid. And I'll point out, I'll just reiterate the fact that there was a decrease in this when people went low-fat vegan. So these are low-fat vegan diets for 2 days. The mitochondria get fragmented. You give them back stearic acid, they fuse. Again, the broad strokes painting here, carbohydrates do not cause insulin resistance, but in the setting of insulin resistance, they can fan the flames. If you are insulin resistant, limitation of carbohydrates could be very helpful for you. But you have to make sure you eliminate the main thing, which is causing the insulin resistance, which I believe is pretty darn clear. Excess omega-6 in the diet, you want that to be less than 3 to 4% of your diet. That's the evolutionary level, I believe. If you go more than that, your body's going to think winter's coming and you get fat. Again, this is a much deeper rabbit hole. I'll go further on my podcast in the future. Stay tuned for that. I've talked about it on my social media. Ben has some good questions, doesn't he? This is intense. Hope you guys are enjoying this. We're coming to the end here. I'm going to wrap it up just because we've done a lot already. But I want to talk about a few more key points. So the next question Ben asks is, you say meat is not associated with cancer, and I definitely do not believe it is associated with cancer. There's a whole chapter in this about how it's totally wrong to say that is the case. And he says, what would you change if you had cancer? So in answer to this question, I would direct the listener and the watcher to a podcast I did with Al Dannenberg, who is a 44-year veteran of, he is a dentist who specializes in tooth and gums, which is known as periodontics. And he has been diagnosed with kappa light chain multiple myeloma and has been doing a carnivore diet for the last 6 months and now has some of the best quality of life that he's ever had, especially since his cancer diagnosis in 2018. And on his last PET scan, he was free of cancer. So in this one N of 1, there was a very clear improvement in his quality of life, and his cancer is dormant. He's not saying he's completely free of cancer, but on his PET scan, on his positron emission scan, there's no active cancer in the setting of tons of meat. It's not as simple as mTOR fuels cancer. It's more complex. And as I talked about on the previous podcast, one of the main problems with cancer is cachexia, the loss of lean muscle mass. It's very concerning to me that most mainstream oncologists are recommending the removal of protein from the diet in cancer. These patients are going to get very cachectic, and this is going to accelerate decline. I also want to share a couple of case reports that are done with a carnivore diet. Yes, there are published case reports with a carnivore diet in patients who have cancer. These are single case reports. There's no long case series, but I hope that in the future there will be much more research on this way of eating. But I think that even these case reports begin to show us that it's not as simple as red meat equals cancer or red meat and leucine equals mTOR equals cancer. It's much more nuanced. Probably has to do with immunologic tolerance, which we know is connected with gut permeability, and that is something that can certainly be improved with the removal of plant toxins. So I want to show a few of these case reports. Here is one, halted progression of soft palate cancer in a patient treated with the Paleolithic ketogenic diet alone, 20-month follow-up. PKD, the Paleolithic ketogenic diet, is a carnivore diet. It's a group in Hungary. They call it PKD, but this is showing that the patient has been on the diet for 20 months without symptoms or side effects, and they conclude it's safe and effective, and the tumor progression has been halted in that patient. Certainly not worsened. Really interesting study there. Furthermore, they have published other case reports looking at rectal cancer. So treatment of rectal cancer with a Paleolithic ketogenic diet, 24-month follow-up. Again, the same thing. The patient postponed surgery for 2 years on the PKD diet. So Paleolithic ketogenic diet, a carnivore diet. When the patient was strictly adhering to the diet, the tumor regressed. It looks like adherence was somewhat difficult in this patient, admittedly, but this is suggesting that with adherence, the tumor did not progress on this diet and actually regress. Now, I am not suggesting that anyone forego mainstream medical care of your cancer. Talk to your oncologist. Certainly, this is not to be misconstrued as medical advice, but I think these studies show that carnivore diets, animal-based diets, at least in these case reports, do not accelerate cancer progression. I would think they are totally safe in this situation. Complete cessation of recurrent cervical intraepithelial neoplasia by the Paleolithic ketogenic diet, again, carnivore diet, which is nose to tail and includes organ meats. They say they conclude the diet safe and effective, patient avoided hysterectomy, and that the high-grade squamous intraepithelial lesion was totally normal in 26 months. Sometimes people with this cervical intraepithelial neoplasia clear it on their own, but the evidence is pretty clear that, at least in those cases, in an owl's case, it doesn't worsen it. So I would definitely eat nose to tail in this situation, getting all the nutrients you need, and I would be very careful to maintain adequate gut health. And I would, again, listen to the podcast I did with Al Dannenberg. We talk all about that in there. Ben's next question has to do with epigenetics and longevity. On page 169, I talk about an observational study showing that telomere length was directly correlated with meat consumption. Again, it is observational, so we can't draw a causal connection, but there is a strong correlation here between this increased intake of red meat and longer telomeres. So Ben says, are there any studies looking directly at telomere or Horvath clock responses to plant versus animal intake that are larger, more robust, or non-observational? So there are some, but nobody has done an interventional trial with meat. There have been some interventional trials with meat nutrients, specifically folate and B12, but there are some trials that further suggest that meat is not shortening telomeres, and I will show some of those, and some trials that show that other foods in the plant kingdom don't seem to lengthen this telomeres. Horvath clock has to do with CpG islands and how they are methylated, and no one really knows what's going on with these right now. There's a little bit of study with this. I'll show one study with the Horvath clock. In fact, I reached out to a company, My DNA Age, and I'm going to do a Horvath clock test on myself in the near future. I will let you guys know the results. They probably will not be back by the time this podcast airs, but I'm going to look at My DNA Age, looking at the epigenetic methylation of these CpG islands. Let's start with telomeres, and I will show you guys the research there beyond the one observational study I mentioned in the book, which suggests that red meat is associated with longer telomeres. And the point I make there is red meat doesn't seem to be associated with shorter telomeres like everyone says. All right, so processed meat, but not unprocessed red meat, is inversely associated with leukocyte telomere length in the strong heart family study. Again, this is more observational epidemiology with its attendant limitations, but the non-processed meat was not associated with shorter telomere length, suggesting meat doesn't shorten your telomeres. And like I said before, some studies have shown that it actually lengthens your telomeres. Here's another observational study looking at the effects of telomere length on looking at the effect of telomere length in connection with different diets. So this is a systemic review and meta-analysis. They looked at many different diets, and they found that there was no effective diet on telomere length. And they looked, but they didn't really look at any studies that looked at meat. So you can see the different interventions here. There was a low weight diet, there was a low saturated fat diet, there was a Mediterranean diet, a carbohydrate, alpha-linolenic acid, PUFA, omega-3 supplement. A lot of them, there was a whey protein, navy bean powder supplemented, rice bran supplements, cruciferous vegetables. None of these lengthened telomeres. So none of them really had any effect on telomeres with these foods. Unfortunately, none of the foods studied were red meat. So again, that's interesting. So nothing lengthened telomeres within the plant kingdom, but one of the more interesting studies I found looked at actually an intervention in which nutrients were given. And it looked at the Horvath clock, which again is CpG methylation islands. So this study is dietary intervention modifies DNA methylation age as assessed by the epigenetic clock. And what they did was they gave people folic acid, which is unfortunate because I think that a more biologically uh, relevant form of folate would have been better, like methylfolate or others. And they gave them B12, and they gave them flavanols, which is interesting, two different groups. So the flavanols were the monomeric or oligomeric flavanols. And the results are summarized in this graphic here, that when they gave people folic acid and B12, which are nutrients that, well, B12 only occurs in meat, and folic acid could occur in leafy greens, but is much more bioavailable in liver and organ meats. Again, the importance of eating organ meats. There was decelerated methylation age in females with MTHFR 677 C to T. And that's exactly the polymorphism that I have. I am also homozygous for MTHFR. And personally, I have been able to maintain my homocysteine very low by eating plenty of riboflavin, whereas riboflavin, it's in organ meats, liver and heart. Good luck getting riboflavin in plant foods. But I found it so interesting that the decelerated DNA methylation age happened with nutrients that are found in meat. And when they gave them the flavanols, there was the opposite effects. These are plant compounds actually caused hypomethylation. So the plant compounds were affecting these DNA methylation enzymes differently than folic acid and B12. And as they suggest here, perhaps in a negative sense. Now, the CpG methylation islands are quite complex, and there are many algorithms that we use to interpret these. But in this study, nutrients found in animal foods decelerated DNA methylation age directly, especially in those people with MTHFR polymorphisms. I suspect this effect would have been even stronger had they used riboflavin, and there is essentially no good way to get adequate amounts of riboflavin from plant foods. That's not opinion or conjecture. That is a nutritional fact. The one thing that I'll also just mention here is that there's never been an interventional study to suggest that red meat is in any way, shape, or form inflammatory. And there are multiple studies in the book that I note, like this one, which show that increasing red meat does not elevate markers of oxidative stress. In this study, there were, which is an 8-week parallel design, the participants replaced energy from carbohydrates with 200 grams of red meat in their diet, and they found a trend for lower C-reactive protein and no differences in the concentrations of F2 isoprostanes, serum amyloid A, or plasma fibrinogen. Our results suggest a partial replacement of dietary carbohydrate with protein from lean red meat does not elevate oxidative stress or inflammation. If anyone tells you that red meat is inflammatory, they are not telling the truth, or they are showing a study that I have never seen, because I am not familiar with a single interventional study that shows that red meat is inflammatory. End of story. And I think, as is illustrated by that one Horvath clock study, the nutrients found in red meat are critical for methylation, which is what is essentially happening at the epigenetic level for our DNA and what is being looked at by epigenetic Horvath and other clocks examining these CpG methylation islands. If you want nutrients, you need animal foods. You can get suboptimal levels of those nutrients from not quite as bioavailable sources in plant foods. But again, in my opinion, this is the thesis in my book, animal foods are king. They are the superfoods. And I thought it was so interesting that in that study, the methylation patterns showed decreased DNA age in nutrients that are rich in animal foods, and the reverse when they supplemented with the flavanols. All right, you guys, we are almost to the end of our journey together. I hope that you will check out my book, The Carnivore Code. I'm going to wrap up with a few lightning round questions before this gets to be too onerous. I love talking about this stuff. I totally appreciate Ben giving me all these amazingly good, detailed questions. I hope this has been helpful. Again, this is all in my book. I've included some studies that are not in my book to enhance the detail in this podcast. These solo casts are always challenging, but I hope it's brought value. If you're curious about this, if you find value in my work, please check out The Carnivore Code, which is out now. The second edition is out. My hope is not that people will stop eating all plants, but that we will help people understand that they do not need plants in their diet if they're suffering, and that for some people, the removal of many or all plants may result in significantly increased health. Certainly, I believe that I would not be putting words in Ben's mouth if I said that he had experienced that in the past, and he had improved GI symptoms and felt better by eliminating some of the plants. He's talked to me about eating a carnivorous diet. I don't know exactly how he's eating now, I'll let him comment on that in the beginning of this podcast, but I think that there are tenets in this book that are super important for all people, even if you don't want to eliminate all plants. But it's important to know that plants do have toxins and that red meat, incredibly valuable and full of nutrients that help us maintain insulin sensitivity, as I talked about throughout this podcast, and help us maintain apparently a lower genetic age at the epigenetic level. I think there's a strong argument for that. So a couple last questions. Page 219, he says, you say that fruits are seeds coated in natural candy, but can we eat fruit flesh and leave the seeds behind? Absolutely. I think that, as I said, tier 1 carnivore diets can include fruit. If you are not insulin resistant, you can include carbohydrates in your diet, but do not eat the seeds. I think the seeds are full of toxins, lectins, oxalates, phytic acid, etc. All right, so on 286, I say I have a preference for unrendered fat versus rendered fat. I think that both are good. My preference for unrendered fat is just that a lot of people who are eating rendered fat often get a strong, let's just say, bile response, biliary response. And if people cannot tolerate fat, the unrendered fat may be better. But I think if you can tolerate rendered fat, it's fine. And I would choose tallow as the main fat because it's going to be higher in stearic acid. And that is what we made into that fire starter supplement, a high stearic acid oil, which, as we saw earlier, was beneficial at the level of visceral fat, which clearly controls whole body insulin sensitivity. Page 288, Ben says, you say oleosins from coconut and olive oil may cause an allergic reaction. How conclusive is that? I think it's anecdotal. Oleosins are protein fragments in oil. So people often say, what about coconut oil? What about olive oil? I think they're fine. They're way better than vegetable oil. But I think that really what you want is animal fat above all their fats. If you want to put an oil on your salad, olive oil is probably okay. I think the jury is still out on how monounsaturated fat in such high amounts can affect the visceral adipose tissue. I think the concern would be that if you are stearic acid deficient, you may have a problem there. But moderate amounts of monounsaturated fat are probably fine. We're still learning here though. So again, my preference is for tallow. Ben mentions that he has come across some studies noting concerns with saturated fat and endotoxinemia or endotoxemia, which is the increase of lipopolysaccharide in the blood after saturated fat. And I've talked about this on previous podcasts, on my podcast with Tommy Wood. The takeaway here in this lightning round is that in the setting of dysbiosis, increased saturated fat can cause lipid rafts. In the setting of a healthy gut flora, saturated fat is not going to cause endotoxemia in any way, shape, or form. So it's dependent on the gut flora of the individual. And if you have dysbiosis, sometimes a lower fat diet is better in the short term while that is being cleaned up. Again, I've talked about that in more detail in the past with Tommy Wood, but there is no evidence that saturated fat from animals is going to cause inflammation or endotoxemia in someone with a, quote, healthy microbiome, which you will know if you don't have GI symptoms and you poop regularly every day. I've talked about this on multiple podcasts, but just in case anyone's wondering, I do not have fiber in my diet. I eat a nose to tail carnivore diet with lots of organs, and I poop every day. You do not need fiber to poop. I've gone into detail about that multiple times. There's a whole chapter in my book about that as well. And the reason that I include honey in my diet is something I've discussed on a recent continuous glucose monitor podcast. I wore a continuous glucose monitor from NutriSense for about 2 months. Really enjoyed it, learned a lot about my blood glucose responses. I did not become insulin resistant by including honey in my diet. I think of it as an animal-based carbohydrate, quote unquote, slightly tongue-in-cheek. And I found that my electrolytes were just much easier to maintain with some insulin spike, which goes back to the previous discussions of, are all insulin spikes bad? No. Insulin spikes are totally normal as long as you are metabolically healthy. If your metabolism is broken, if you have underlying insulin resistance, then those insulin spikes are going to be disordered because your body's not going to respond to them because you have insulin resistance at the cellular level. Again, I think the main driver there at the molecular level is polyunsaturated vegetable oils. So in my case, you can see this on the CGM episode on my podcast. My blood sugar goes up, it comes back down quickly, and my baseline is 60 to 70 all the time. I did not become insulin resistant with over a month of honey every single day, and I feel better with it from an electrolyte perspective. So this is the other flexibility of a carnivore diet, is it doesn't have to be low carb or ketogenic. lots more there on my podcast if you have questions. So, all right, you guys, thank you so much for tuning into this podcast. Thanks for Ben for having me on. Please check out my book, The Carnivore Code. If you have trouble getting organs into your diet, please check out Heart and Soil, heartandsoilsupplements.com. We have liver and bone marrow, beef organs. We're going to have Firestarter out soon, as well as a blood builder supplement. We've got a lot more of those coming soon. I don't, necessarily, advise that you guys should take organ supplements over the real thing. But if you cannot get the real thing, the organ supplements are definitely an adjunct. I take them every day to fill in the gaps. For a lot of people, eating liver and these other organs is difficult, traveling, etc. I think these fill in a real gap in human nutrition. And the goal is just to get more people healthy. So if you can eat real liver, do that. And if you can't, check out the desiccated organ supplements we are making from New Zealand, from grass-fed, grass-finished animals. Check out my book, The Carnivore Code, thecarnivorecodebook.com. Thank you guys for your support. Check me out. So thecarnivorecodebook.com, or my website is CarnivoreMD, where you can find all of my stuff. Thank you all. Stay radical. Until next time, I love you.